Bienvenidos, Ushamadid, and welcome UMGC learners from the CMIT-455 Section 6380 course for the spring 2021 semester. This is the CCNP ENCOR version 8 curriculum from the Cisco Networking Academy, and in this packet tracer tutorial, we're going to be taking a deep dive look at packet tracer activity 16.2.2, where we're going to be configuring and verifying site-to-site IPsec VPNs between two routers using the CLI. And in this video, we are going to be going deep into the IPsec suite of protocols. We're going to be talking about Isocamp. We're going to be talking about IKE. We're going to be talking about Authentication Header and Encapsulation Security Protocol. We're going to be looking at Diffie-Hellman groups. There's a lot of information that's going to be covered in this video, so please make sure that you are ready to go. So, first things first, let's take a look at the topology as it exists in our activity. And so you can see we have a simple topology here, and the first thing I want to point out is that they're using RFC 1918 addresses. Now, there's nothing wrong with running an IPsec VPN tunnel between two internal routers, if that's something that you wanted to do. More realistically, this is something that would be done if, for example, you could say that this location here was in New York, and this location here is in California, and we want to encrypt the data. We want to provide confidentiality, integrity, and authentication. So the CIA, that triad that you hear a lot about in different security contexts, right? So confidentiality, we get that through the encryption. It's about obfuscating all of the data, right? Encrypting the data. That's the C in CIA. And then you have the I, which is integrity. And we're going to get the integrity using hashing algorithms, right? Whether it's SHA, HMAC, whatever the case may be, we're going to use hashing algorithms to ensure that none of the data has been changed or manipulated in transit. And then we're going to use IKE, the Internet Key Exchange Protocol, in order to provide authentication. Excuse me. And the authentication is making sure that the endpoint that I think I'm talking to is the actual endpoint, right? So that router 1 and router 3 have confidence that they're both talking to router 1 and router 3 respectively, right? That they're not maybe talking to router 2 who could be stealing some information, right? So that's the CIA. Confidentiality is the encryption. Integrity is the hashing. Authentication, we're going to be using a pre-shared key to set this up using IKE. And then a secure key exchange. And that's where Diffie-Hellman's going to come in. Now, let's be clear. IPsec is not a protocol, right? When someone says, oh, hey, I'm running IPsec, well, that can mean a whole bunch of things. And this is usually one of the first confusing things for learners is that they think that IPsec is a protocol. It's not. IPsec, think of it as like an umbrella. It's a suite of protocols. And that's what makes IPsec so flexible, is that new protocols could be added in, right, as time moves on in order to make the concept of IPsec more secure. But again, IPsec in and of itself is not a protocol. It's a suite of protocols. Now, we'd have to go back to the RFCs that originally came out, and there are a number of them. Let me clear the screen here. There were a number of them that came out from, I think it's 2401 to 2412 or 13. I think it's to 12. But you can see that this is 2401, right? And this is sort of a high-level security architecture for the Internet Protocol. Now, look at the date on this, right? You can see it's November 98. And if you were around back then and old enough to remember what was going on, the internet was kind of starting to explode, right? And had really exploded onto the scene 95, 96, 97, 98, and things were starting to go crazy. And that's when people started to ask the question, well, there are bad actors out there, so we need to come up with a way to protect the information that might be traveling over the internet. And so it was right around November of 98 when this RFC came out, and during 1998 when all these conversations started to happen, that you had a series of RFCs, like the IKE v1 RFC is 2409. So if I was to switch here to 2409, and that's what I'm familiar with, and you can see it's been obsoleted, right? So the newest version, and it was obsoleted by that, and then we've got some updates. So the newest version, right, which covers IKE v2, which we'll be talking about, excuse me, is now RFC 7296, right? So that Internet Key Exchange Protocol, right? So it started with IKE v1, and we're going to talk about IKE v1, and that's the configuration we're doing in this activity. We'll be using IKE v1. Now, what is the Internet Key Exchange Protocol, right? So IKE is just simply a key management protocol. Now, it is part of, or it uses a framework referred to as ISAKMP, ISAKMP. And these are two terms that when you're dealing with IPsec, you will repeatedly see these terms, IKE and ISAKMP. So remember, IKE is the Internet Key Exchange Protocol. It's a key management protocol. Now, there's two versions we've already seen. There's IKE v1, which is sort of legacy, and then there's IKE v2. And you should probably be using IKE v2 on any greenfield type work, and it is supported on older routers, but IKE v2 is where you want to be. Now, there's a framework that is leveraged by IKE, by the Internet Key Exchange Protocol, that's called ISAKMP, ISAKMP, which stands for Internet Security Association Key Management Protocol, okay? And it basically, what ISAKMP is, just like IPsec is kind of like a framework, like an umbrella underneath which a lot of these protocols that we're going to discuss sit, ISAKMP is kind of the same thing. And what it defines is the requirements to build a security association between, an SA is what they refer to it as, between devices, right? So IKE uses ISAKMP for key negotiation, right? And so here's where a lot of terminology can kind of make this a little complicated. We'll try to make it as easy as possible. So remember that. IKE v1 and IKE v2 are both protocols. Obviously, v2 is newer, and so this is probably where you want to be for greenfield deployments because there's a lot of enhancements, and we'll talk about a lot of the similarities and differences as we move throughout what are going to be 3 videos here, right? I'm going to do this video on Packet Tracer, and then we're going to be using crypto maps here. But then I'm going to show you how to do a static virtual tunnel interface. And then we're going to do GRE over IPsec. So then we're going to do a tunnel over IPsec using GRE, right? So IKE v1 and IKE v2. Just remember, it's all about the key management. And ISAKMP is the framework that IKE uses to perform that key negotiation between the two endpoints. And in our case, it's going to be router 1 and router 3. So let's take a step back over here to the activity, and you can see they provide us with a bunch of information, and this is where you're going to start to see all of this terminology here. So, ISAKMP Phase 1. Now, here's what's interesting. You will, in a lot of cases, hear this referred to as IKE Phase 1. And this is where it can be a little confusing, is you hear IKE Phase 1, and sometimes you'll confuse it with, oh, IKE version 1. Well, no, it could be IKE v2, right? So the version of IKE is 1 or 2. There will be 2 phases that we go through when we establish the security association, that VPN, that IPsec VPN tunnel between router 1 and router 3. The first phase is phase 1. And phase 1 is all about ensuring that we have the key exchange, a secure key exchange between the two nodes. So I want you to think of the analogy like this. Phase 1, and again, you'll hear Isocamp and you'll hear Ike. So it's either Isocamp phase 1 or Ike phase 1. You're saying the same thing, right? People are saying the same thing when they say phase 1 with Isocamp and Ike. If they say Ike V1, that is very different from Ike V2. So keep that in mind. So Isocamp phase 1 is all about the exchange of the keying material. Because remember, we're dealing with symmetrics encryption algorithms here, symmetric algorithms, which will require a shared secret key. And that shared secret key has to be communicated securely, right? Because you wouldn't post, think of it like this. If you wanted, your wife or your partner to log into your Gmail account and, let's say they're on the road, you wouldn't send the password to that account in an email that's not protected, right? Or you wouldn't post that on your Facebook page saying, oh, hey, honey, here's our password for our Gmail account. And you put that on your Facebook page. That doesn't provide much confidentiality in terms of that password. And the same is true here. And we're going to be using pre-shared keys, which is just basically a fancy way of saying we're going to create a password that's a string, right? It could be ABC123, whatever the case may be. But again, phase 1, Ike phase 1, Isocamp phase 1 is all about creating and defining the parameters to facilitate the secure exchange of that shared secret keying material. And then let's dive into this activity now. So we've got all these settings here, and we're going to come back to a lot of these. And you can see here, now they refer to it, and it kind of makes it even more complicated. You see where they say IPsec phase 2, right? Well, typically you're going to hear either Ike phase 2 or Isocamp phase 2, right? And sometimes you hear IPsec phase 2 as well, right? But I typically try to stick with one. I always say Ike phase 1, Ike phase 2. Right? You see, I almost said Ike V1, Ike V2. So I try to say Ike phase 1, Ike phase 2, right? But again, the phases are very different from the versions of the Internet Key Exchange Protocol, Ike, right? So let's go ahead and dive in here. Again, they've got some pre-configured passwords, which not a big fan of. And so the first thing that we need to do on router 1 here is on the ISRG 2s, which is what these are. These are 2911s, I believe. We need to enable the security K9 license. And the same is true on physical Cisco routers. Now, I'm going to give you a great little hint here. If you pick up a 2911 or a 3900 series or a 1900 series off the internet to put into your lab, this will activate the security license so that you can do all these things. And it's a right-to-use license. And so I think they give you 8 weeks to use it out of the gate. Again, it never expires on you, and you're supposed to true up that, right? You're supposed to actually pay for it. But if you didn't, then you would be okay to continue to use the license. So let's get the password in here. So the console line Cisco Con PA55. And I'm sorry, they're 1900 routers because we have the C1900 package down there. All right, so we need to activate the security license. Because if I go into privilege exec, and I do not like this part here, and where's the enable password? Cisco ENPA55. All right, so I'm in privilege exec. If I was to go into global config, and if I scroll down a little bit here, you'll see that they're going to provide us, right, with the access list command. And I'll talk about why we're doing this crypto map. And again, this is kind of the legacy way to handle the IPsec site-to-site tunnel, is using crypto maps. Not to say that there aren't use cases for it. However, static virtual tunnel interfaces are probably more popular than the crypto map approach, because with a static virtual tunnel interface, we don't need ACLs. So let's go ahead. If we were to say crypto Isocamp, Isocamp policy. You can see it's not there, right? As soon as I say crypto, you can see we have key, but there's no Isocamp. And you'll see this exact same behavior on a real Cisco router without the key applied, without the license key command applied. This is what will end up happening. So what do we want to say? We want to say license, boot, module, C1900, technology package, and let's see if they list them all out. Well, it only lists out the security one, right? Now, there's a data K9 package. If you wanted to mess around with MPLS, you could apply that license and you would be able to do MPLS. All right, so license key boot, and then we'll say security. Now, here's the EULA agreement, right? Stating that, hey, you've got it for 8 weeks or whatever the time frame is. And then after that time frame is expired, we are expecting you to true up that license key and actually get one from Cisco. All right, so we've got it. Let's go ahead and say write mem. And do we need to do this on router 3? I'm wondering if they're going to have us do this on router 3. Give me 1 second here. Because if they are going to have us do this on router 3, if it hasn't been enabled, we'll do it on router 3 as well. So we'll go ahead and say, again, reload. So we'll reload router 1 after we've applied the key. We'll come over to router 3 and let's apply the key as well. And so remember, the first step, Cisco Con PA55, Cisco ENPA55. See it? I think I missed typing here. CO ENPA55. There we go. Get into global config, license, boot, module, C1900, technology package, security K9, and then we say yes. All right, we'll say end, write mem, save our config. Let's make sure we got that in there. There we go. And then reload. And so that's kind of the first step. If you don't already have the security license on there, you need to make sure that you apply that security license like we did right here. So we're doing crypto maps. And again, crypto maps are sort of the legacy way to do site-to-site IPsec VPN tunneling between routers, because Cisco Con PA55, hold on, let me get back into privilege exec here. CO ENPA55, there we go, is kind of the legacy way to do it because of this access list creation. So remember, we're going to be applying the policy, the crypto map is going to be applied on the physical interface here, right? Now, and this is why, by the way, if you're wondering, well, why do they have this up here? What's the purpose of this? Remember, if I apply a crypto map on that interface and I'm not specifying the specific source and destination that I want encrypted, then everything is encrypted. And I want you to think about that for a second, because that means all traffic that leaves router 1 and when we applied it over here to router 3 would be encrypted. The problem with that is that router 2 has nothing to do in the LAN over here. We're not doing IPsec to router 2. So what we're doing with the crypto map is we're identifying the traffic to and from source and destination that we want to be encrypted using all of these settings. And so basically we're going to be creating an ACL on router 1, and we're going to be creating an ACL on router 3. And that's where, after we create all of our settings and everything and we apply the crypto map knows to reference the ACL, and there'll be a match address statement in there where it knows to match that ACL or reference that ACL to determine, is the traffic source and destination matching the crypto map match address statement? And if it is, then I encrypt it. But traffic going from PCA to PCB would not be encrypted because it's not going to match the ACL. And again, there's my source network, and that's the network the traffic is going to. Now, at a later date, can I throw another access control entry, another ACE, onto the ACL 110? If I wanted to set up IPsec, here and here? Sure. And then what about here and here? Absolutely, right? So you could definitely do that if you wanted to. So there's nothing that says that I can't adjust things at a later date, right? So let's go ahead and get back into the command mode here, and let's jump onto router 1 and let's hammer out this ACL. So we're using an extended ACL, and it's going to be an extended numbered ACL. So access list 110 permit IP, right? So we're allowing all IP traffic. Now, remember, we're going to talk about two protocols here in just a second. The first is going to be Authentication Header. And the second is going to be the Encapsulation Security Payload, or ESP. Authentication Header, people just say AH. And ESP, or Encapsulation Security Protocol, you hear is just ESP. So these are two protocols under the IPsec umbrella that get used, or that can be used, and you're typically choosing one or the other, and the majority of the time you're going to be choosing ESP, and we'll talk about that in a second as to why that is. But typically that's what you're going to see. And so ESP is IP protocol 50, and Authentication Header is IP protocol 51. Those are the IP protocol numbers, but ESP and Authentication Header, these are layer 4 protocols. They're layer 4 protocols, just like ICMP or UDP or TCP. ESP and AH are layer 4 protocols, and here's what's very different about them. They don't have port numbers. And you might be saying, well, why would you bring up the port number thing? And this is going to be important when we start to talk about IPsec and NAT, Network Address Translation, because that's where things, again, can get a little more confusing as to how does NAT work, or can NAT work with Authentication Header? Can it work with ESP? How does it work with those protocols if there are no port numbers to identify ESP and AH? And so again, we'll dig into that as we move through here. So again, first things first, let's identify the traffic that we are going to be matching. So and again, remember, permit IP means you're permitting everything. So all traffic from the 192.168.1.0, and then we throw our wildcard mask in here for a /24. That's our source network. So any traffic from that network going to this network, .3.0, right? We're going to match that traffic. That's what that ACL is going to be used for. Now, remember, in the course, we really haven't gone over extended ACLs yet. That comes in a later chapter. But know that just because I've created that ACL, that doesn't mean anything. That's just simply an ACL with a single ACE that's been configured on the router. Until I apply this in some form or fashion, either on a VTY line or on an interface or as part of a crypto map, it's not being used. It's just sitting here, right? All right, so that takes care of that, and that's how we're going to match our traffic. And so again, we could do the same thing over here. In fact, let me get logged in. Cisco Con PA55 and Cisco EN PA55. All right, we'll get into global config. And so we're going to go ahead and say access list 110 permit 192.168. Now remember, this is going to switch around because now I'm on router 3. So I'm saying the source would be coming from the router 3 LAN, that 192.168.3.0/24, going to the 1.0 network, or over to over to PCA. So access list 110, permit IP 192.168.3, going to the 192.168.1. And, for permit IP, sorry about that, left out the IP. I was looking up at the IP address to make sure I had the right address. And so there we go. All right, so now we get down, and you'll notice, right, they even refer to it here as IC Phase 1 Isocamp policy, right? And again, This is where these terms can get a little confusing. But just remember, IKE is a key management protocol, right? And it uses Isocamp to perform the negotiation. And Isocamp, again, is like a framework for building the security association, right? Building that secure tunnel between these two routers. And they give us some hints here. I'm just making sure we've got the crypto key. Okay. And so the crypto key we're going to use, this is a pre-shared key, meaning that we're going to manually configure this on the router. And so the highest Diffie-Hellman group, we'll talk about that in a second. Let's get back over here to router 1 and let's go ahead and dive in here. So now that the security license has been installed, when I say crypto ? Take a look at all the additional options we have now, right? So the crypto IPsec command is there. We've got the crypto Isocamp command, crypto key, crypto map. So all kinds of good stuff going on here, but we needed that security license to make this happen. So I'm going to say crypto Isocamp policy, and then we're going to give it a number. Now, we'll throw a question mark in here. And interestingly enough, this is pretty much extremely accurate to what if I was to come over to a real Cisco router. Again, I've got a 2811. Let's get into privilege exec. And if I was to say crypto, sorry, let's get into global config. And if I was to say crypto Isocamp policy, we'll say 100. We'll make it different. And if I did a question mark, you can see authentication, default, encryption, exit, group, hash, lifetime, and no, right? Authentication, encryption, exit, group, hash, lifetime, no. So we've got pretty much the full suite of things here that we're going to be able to work with. So let's walk through these one at a time. So they actually ask us to do, and it looks like, are they going to go about this? No, they're not going to do it alphabetically. So the encryption. So what did we say the encryption was? This is your confidentiality. And remember what we're talking about. We're not talking about the traffic that's flowing back and forth. This is about the key, the shared secret key. That's what this is all about. And here's how I want you to kind of think of this. Phase 1, Isocamp/IKE phase 1 is all about the control plane. It's about that shared secret key. And we're going to negotiate the exchange of that keying information, and we're going to do it in a secure fashion. And that's what phase 1 is dealing with. Phase 2, I want you to think of the data plane, the forwarding plane. And that's all about the transfer of data back and forth, right? So phase 1 is our control plane. Phase 2 is the data plane. So this is going to provide confidentiality for phase 1, the control plane setup. If I do a question mark, you can see we've got 3 different types of encryption algorithms that we can use. Triple DES is legacy. You should not be using triple DES. And DES, same thing. DES and triple DES, not very popular, right? So AES, that's where you want to be. And so they're actually, I'm glad that they're showing this here. So we'll say AES, I'll do a question mark. You can see that it goes up to 256 bits for the key value. All things being equal, the more bits, so the higher the number of bits in your key, the more secure, theoretically, your tunnel is going to be. Again, if you give your key to people, it doesn't matter how many bits you have in your key, it's not going to be too secure. So you can see here, if I say encryption AES, I wanted to do a question mark here, you can see it's the same thing. And this is 15.1 code. It goes up to 256 bit keys. And so we'll say AES 256. The authentication. So remember, what did we say the authentication is all about, right? The A in CIA. And this is about the shared secret key. Right? How are we going to authenticate this? How am I going to prove, how are router 1 and 3 going to prove to each other that they are who they say they are in the exchange of these messages? And we'll talk about main mode and then aggressive mode, because there's 2 modes. Again, we're doing IKE v1, Not phase, this is phase 1, but we're also IKE V1 is how we're doing this configuration. So there's a main mode and there's an aggressive mode, and I'll break those down in just a second. But this authentication is how are router 1 and 3 proving to each other that they are actually who they say they are. And it's that we're using this pre-shared key, right? So we say authentication pre-share. Now comes the group. And this is the most important part to understand here, because there's a huge misconception that these are the groups that you should be using. To be clear, right? To be clear, Diffie-Hellman group 1, 2, and 5, which are 768 for group 1. These are bits, 768, 1024, and I believe 1536 bit keys. All of these are very legacy. In a current install, you should not be using any of these Diffie-Hellman group numbers. In fact, Cisco has recommended that as of 2012, you should, so 9 years ago, you should have stopped using these, right? Now, we're doing it here in this activity, not a big deal, but no, in reality, these are not the group numbers that you want to be using. And so if I was to come over here to a real Cisco router, and again, this is 15.1 code, and say group and do a question mark, you can see we have many more choices. And you can see, and so 768 bits for 1, 1024, and 1536 for groups 1, 2, and 5, right? Very old, very unsecure. 9 years ago, you should have stopped using these. So don't use those, right? And if you are using them, think about maybe changing them. Now, 14, 15, and 16, you can see that these have many more bits, and these are much better. However, Cisco best practice is saying as of 2030, so just 9 years from now, you should not be using 14, 15, and 16 anymore. Now, we've got 19, 20, and 24. And again, it's sort of the same concept. The higher the group number, theoretically, the more secure it's going to be. So you want to make sure that both routers on each side here, because again, this is a point-to-point, site-to-site IPsec VPN tunnel that we're creating. You want to make sure that this router may have Diffie-Hellman Group 24 support, but does the other router, right? Maybe the other router's a little older, the iOS might be older, but in general, modern day routers are going to have Group 24. In fact, they even go into some elliptical curve cryptography, ECP, I believe is how they refer to it, and which is even more secure, right? And I think that might be Group 21 that doesn't actually even show here, right? So again, the higher the number, typically the better. And you can argue use case, right? Well, how important is the material that you're trying to protect here, right? Your keys are pretty important, so you want to make that choice. So here they ask us to do group 5, right? So we're just picking the most secure group. Now, there were some other options here. Lifetime. How long do you want to allow this lifetime to live, the security association to be established before it rekeys? Right? I think it's 86,400 seconds is the default, which is 24 hours before it's going to try to rekey, right? And then you've got the hash. And this is a hashing algorithm that you could use. Remember what we said about the hashing algorithm? That's your integrity. So typically, if I was to say hash, they don't have us, oh, I already bumped out of we'll come over here and do it. Typically, you're going to set up a hashing algorithm like SHA-512, right? Again, you're not going to use MD5 and you're not going to use SHA. You're going to be using one of these three here. And again, higher the number, theoretically, the more secure it's supposed to be. That's what you want to go with. Again, it depends on how much traffic you're passing, CPU overhead, but most modern day routers, they're going to be able to handle whatever it is that you're doing. Okay, so They don't have us doing the hash. They just have us doing the group. And then that is it. So now we're going to go ahead and we're going to say crypto Isocamp. And we're going to put the key in, right? So here is that pre-shared key, VPN PA55. Then the next thing we're going to put here is the address. So who am I going to share this key with? Now, a lot of times you will see that as the value. Now, that's not going to get us points here. And what that means is, well, I'm open for anybody to try to establish an IPsec VPN tunnel with me using this key, this shared secret key, VPN PA55. And again, right, I've used this before. It's, you know, you can use the exact IP address. I've used the quad zeros before. Using the quad zeros means, hey, somebody else could sit there, and if they knew the key, then they might be able to set up a tunnel with you. Again, these are all things you're going to have to weigh in your decision-making process. But the most secure way to do this is to say 10.2.2. That is basically going to be the only IP address that I'm going to communicate with in order to set this up. And I wanted the address keyword in there. I forgot about that. And there we go. Right? So now those are, so right there, full stop, that is your IKE/Isocamp phase 1 configuration. Those are the configuration parameters that have been defined to protect and obfuscate and encrypt the keying material between router 1 and router 3. Because remember, they have to share this secret password somehow, and we have to make it secure. And we have to make sure that they can authenticate each other to determine, hey, is router 1 actually router 1? Is router 3 actually router 3? So now we've defined all of that. If I say do show run, we've got all of that defined right here. There's our Isocamp policy for phase 1, and there's my shared secret, right? So we're all ready to go here with phase 1. So now, and you'll notice they even say step 5, configure the IKE phase 2 IPsec policy. And in fact, let's do this. Since we just did the phase 1, let's stick it with the phase 1 here. So it's Cisco ENPA55. Not a fan of the passwords being set here. ENPA55. CO ENPA55. Why is it not taking that? Oh, Cisco Con PA55. Sorry about that. And then Cisco ENPA55. Again, proving why I don't like activities that have the password preset. So let's take care of the Isocamp/IKE phase 1 configuration. And let's just say crypto Isocamp policy 10. We're going to say encryption AES 256. We're going to say authentication pre-shared key, because we're going to use a pre-shared key. We're going to use Diffie-Hellman group 5 in order to protect that key and material. We're going to exit out. We're going to say crypto Isocamp key VPN PA55, and the address is going to be the interface of router 1, right? Remember, the 10.2.2.2 is router 3's serial, what I'm assuming is going to be 000 or 010 interface here. We need to figure out what is the serial interface on router 1, and we have an addressing table, and it's 10.1.1.2. So I'm glad I looked at that, because I was getting ready to say 10.1.1.1. So we say 10.1.1.2. And now phase 1 has been configured on router 3. So let's come back over here to router 1. So we've got phase 1 configured on both sides. Isocamp IKE phase 1 configured. We're done. So now we need to deal with phase 2. And these will be the IPsec policy configuration commands, where now we're going to be configuring, excuse me, a transform set is what they refer to it as. And so actually, before we step into that real quickly, the main mode and the aggressive mode that I mentioned, right? That takes place as part of phase 1 when the keying material is being exchanged. Now, obviously, you're probably thinking aggressive mode must be quicker, and it is. It's the exchange of 3 packets. But the problem with that is the identity of the responder is done first. And the issue with that is that it's not secure, right? It's not a secure way to do it. Main mode, it's basically 6 packets, and it's better against denial of service. It's more secure, right? And you'll hear people say, oh, well, it's a little slower. Well, yeah, it's a little slower, but it's not as if you're going to be waiting for an hour for your IPsec VPN tunnel to come up because you're using main mode as opposed to aggressive mode. In fact, in any government environment that you're in, if you're using Nessus scanning, the security team is doing Nessus scans. This has happened to me where we had IKE v2 configured. Now remember, everything we're talking about is IKE v1. In IKE v2, there is no aggressive mode. It doesn't exist, right? But when the security team scans, they just see that you have an IPsec tunnel configured, right? They maybe, I almost think they're looking for the word IKE. And we got a whole bunch of alerts saying, oh, hey, you need to disable aggressive mode because you're not supposed to be running aggressive mode because it's less secure. Again, when you're using aggressive mode, you've only got 3 messages and the IDs are passed in the clear, right? And specifically the responder is going to be passed in the clear. And so we tried to explain to the security team, we're not running IKE v1. There is no aggressive mode. And we still had to go into the configuration and put in the configuration command to disable aggressive mode, even though we weren't even using IKE v1, right? So chances are you're not going to be allowed to use that in a government environment. And, you know, again, like I said, you're going to be using IKE v2 anyway. And again, we'll talk about IKE v2 as we press on here. So main mode and aggressive mode. And this is where the exchange of the packets are going to go back and forth. And in main mode, the 6 packets, the first 4 of those 6 packets are not encrypted, right? The credentials, right, the encrypted part, the pre-shared key exchange, and the peer ID information, that's in messages 5 and 6. And those are encrypted, right? Again, another reason why you want to use main mode, which is the default, which is what we're using here. So let's go ahead now back to phase 2. So with phase 2, we're going to say crypto IPsec Transform Set, and let me make sure. Let me spell crypto right there. Crypto IPsec Transform Set. And this is just a name, right? What do we want to name it? So we're just going to call it VPN set. You could call it R1-R3. You could, you know, whatever naming convention you want to use, you could use here. Now here is where we're going to define one of the IPsec protocols, either Authentication Header or Encapsulation Security Protocol, and so sometimes I say payload, Encapsulation Security Protocol, ESP, and you can see right here, right? They're talking about AH or ESP. Now, here are the considerations you need to take into account. AH doesn't do encryption, no confidentiality. So the C in CIA with AH is not there. And that usually ends the conversation as to whether you're using AH or ESP, because ESP does do the confidentiality component. It does do the obfuscation of the data. It encrypts the data. And that's why, excuse me, and that's why you will see ESP used instead of AH. Another reason you'll see ESP used instead of AH is that Authentication Header doesn't work with NAT, Network Address Translation. And the reason, and you might be thinking, well, wait a minute, I've heard about this thing called NAT-T, NAT Traversal. Well, when we're talking about NAT-T, we're talking about ESP. And here's why, and again, typically here's why when you're using ESP, if you're using NAT-T, NAT traversal, is because with AH, Authentication Header is checking on the immutable, right? So there's mutable fields in the IP header, and mutable, think of mutation, right? If it's mutable, it can mutate, it can change. And the most popular field in the IP header that can change, and that always is changing as the packet's making its way from source to destination, is the time to live, right? The TTL is going to decrement 255, 254, 253. So that's a mutable field. But Authentication Header checks the immutable fields that are in an IP packet. And an immutable field could be the source IP or the destination IP. And what do you think changes when we do NAT? Yeah, exactly. Network address translation, the IPs would be changing, and that is what Authentication Header, AH, is looking at to determine whether things have been manipulated. The integrity, right? The hashing, checking to see if things have been manipulated in transit. And if you're doing NAT, or if NAT is taking place at some other point along the path, right? You run into trouble there. And so that's where NAT traversal, NAT-T, comes into play. Now, when I gave you the example of ESP, right? If you're doing one-to-one NAT, that was what I just described, right? One-to-one NAT would be IP to IP static NAT, right? AH is going to check the immutable fields. It's going to check the source and destination header. That's why it has issues with NAT. ESP, on the other hand, does not look at the layer 3 IP address information. It's only interested in the layer 4 and the payload. It wants the payload. That's what ESP is interested in. And so, excuse me. And so with one-to-one NAT, ESP works great. But again, how many enterprises do you know that have, 200 desktop PCs and they're doing static NAT for those 200 PCs? So again, when it's one-to-one NAT, you basically have issues with AH, period, right? With ESP, not so much, because ESP doesn't look at the immutable IP header information. So with one-to-one NAT, we're okay. But the question is, how many people are doing one-to-one NAT for everything in their environment? Not going to happen in an enterprise environment. And so then what are you probably going to be doing? Port address translation, or PAT, right? And remember, you might be thinking, well, he just mentioned ports, and I swear earlier you said that ESP and AH, they've got IP protocol numbers, but they don't have ports. So how's that going to work? And that's a great question, because ESP and AH, they don't have ports. So when you're running port address translation, what has to happen, and in fact, with ESP, the only thing that is visible is the security parameter index, the SPI, which is just like this number, right? And then a sequence number to make sure that the encrypted packets are showing up in sequence, and that, there's no foul play going on along the path, and that things are coming in order, right? So the SPI and the sequence number are the only things exposed with ESP. There's no port information. And so the solution to this is NAT-T, and it's NAT traversal. And you might be asking yourself, well, how is that going to work if we're doing port address translation? And the way that it works is that everything gets encapsulated in a UDP packet, because UDP packets do have port numbers. And in fact, if you're doing NAT-T, NAT traversal, you're using UDP port 4500. And that is how you can do NAT with IPsec using ESP. You would use NAT-T. And then to take it one step further, the next question's typically, well, then what do I need to do to set that up? Well, it sort of happens automagically when NAT gets set up and IPsec gets set up, because it will signal it. What it does is it changes the hash inside the initiation packets to basically say, hey, I can do NAT. Can you do NAT? And then there's a response that'll come back and they'll negotiate it out and say, hey, we can do NAT-T. And so then that is how NAT-T would end up working. And NAT-T is covered in RFC, what is it, 39? Give me a second here, 46 RFC, 39, 47 actually. 3947, yeah. Negotiation of NAT traversal in the Internet Key Exchange Protocol. And so, and actually is this, no, so this is actually the current one. And so again, some great information here that explains how the negotiation is going to take place, right? And remember, it's going to be UDP encapsulated, and we're going to be using port 4500. And so that is how you can get away with doing NAT and IPsec. Okay, so here's the IPsec Transform Set. This is for, I want you to think of it as like, this is for the cargo, right? Phase one, and let me see if I can come up with a quick analogy here in my head. Think of phase one as you're negotiating to hire a moving company, right? And they're going to move you from the house that you're currently in to a new house. And phase one is that negotiation process. And ultimately, you write them a check, right? And everybody comes to an agreement. That's your phase one. Phase two, Isocamp phase two, is all about the cargo inside the moving van, right? It's your data. Remember, we're talking about the data plane, the forwarding plane. And so these are the security parameters that are going to be used to protect that. And so what they have us use here is ESP AES. And if I do a question mark, I believe the default, I think it defaults out to 128. But you can see that, again, the more keys that you use in terms of this is the encryption, right? Here's the encryption component, the confidentiality component that's going to allow us to obfuscate the data. Here's the C in CIA. And like I said, AH cannot do the C. It cannot do the encryption. So we do the encryption using ESP. We're going to use AES as the encryption algorithm. And here's the beauty of ESP. ESP can do the authentication or the integrity, right? ESP does the integrity itself. It can do the hashing integrity to make sure that things don't get changed midstream, and we'll use SHA HMAC. And so what I just defined right there was for the data, right? The data plane. This is all that information that's going to be flying back and forth between PCA and PCC, right? Whether they're FTPing stuff or SCPing. This is the transform set and the security parameters and the definitions, the encryption algorithm and the hashing algorithm that we're using to provide the C and the I, right? And that's how that gets done. So now, and actually, before we go there, so let me see if they didn't do it here. Let me see if this is going to be, so I don't have to type all this back out again. I'm going to copy this real quick. And we're going to come over here to a real Cisco router. We're going to get back into global config here. Thank goodness no passwords. All right, so you can see that if I was to pull this back, and I'm assuming we're going to have some more. Yeah, so we've got definitely some more options to choose from here, right? And so, again, GCM is a great option. You definitely want to avoid DES. Avoid DES, avoid triple DES, avoid MD5. You'll notice that we chose SHA HMAC. Do not choose this, right? Again, the higher the number of bits in the key, theoretically, the more secure of a solution you're going to come up with. Now, more CPU intensive? Sure. But again, routers today are very, very powerful. So if I was to say ESP AES and do a question mark, you can see we get kind of the same choices. So if I was to say 256, and then to come over here and say, let's take care of our integrity, right? And we're going to make sure that things don't get changed in the middle. I would say ESP SHA 512, right? We're going for broke. We're taking the biggest, or I should say the largest bit key that we can with that, the integrity check there for our hashing algorithm, right? Now, and take a look. I didn't know that was going to happen. And in fact, I don't, because again, usually SVTIs is what you're going to be using, or you're going to be using, you know, something like EasyVPN, which is DVTI. It's known as EasyVPN, or DMVPN, something like that. But I thought this was interesting that it says Transform ESP256, and that will run with reduced performance because of IPsec Transform VPN Set, right? So again, this is a very old router. I'd be surprised if you were to see this on some of the newer, you know, the 4300s, or, you know, an ASR 1000 whatever, or a 9K. I doubt, I'd be shocked if you saw something like that. You might. But again, you can see that it's going to tell you, hey, you know, you're asking to use the biggest settings that we've got here. We could have some performance impact. So the thing I wanted to show you is you'll notice it put me in the config crypto trans subconfiguration mode. That did not happen over here. Here it left me in global config. And this is the next important point that I want to bring up: the tunnel mode. Right? And when I say tunnel, I'm talking about the IPsec tunnel. I'm not talking about a GRE tunnel. Remember, we can do a pure IPsec tunnel. That's exactly what we're doing here, right? There's no GRE involved, but it's still a VPN, and it's an IPsec tunnel because it's in that tunnel that everything's going to be encrypted and protected. So the mode is what we're interested in here, right? Because this tends to cause some confusion. Now, transport mode and tunnel mode. Keep in mind, when we're talking about transport mode, you're going to be protecting, or the IP is not protected in transport mode, meaning that layer 3 information is not going to be encrypted. It's going to be layer 4 and above. So your IP address information for source and destination is in the clear, right? It is not being protected, right? So it's for transport mode, only layer 4 and above. Now, there's another difference between that and tunnel mode. So with tunnel mode, it's also referred to as IP in IP. So you're encapsulating, and I love how they put this in here, right? Payload encapsulation. That's the data payload, layer 4 and above. That is what is being encapsulated. In the tunnel mode, the IP datagram and above. So layer 3 and above is encapsulated, which is why this is referred to as IP in IP encryption, because we're going to be encapsulating the original layer 3 header and 4, 5, 6, and 7. We're going to be encapsulating all of that, with another outside header, right? So there's more protection that's being done here. And tunnel mode is typically used between two, what you'll refer to as security gateways or security endpoints, right? In this case, it's two routers. It could be a router and an ASA, right? But in this case, it's between two routers. So tunnel mode is used when we're doing a security association between two security endpoints or two security gateways, right? Like routers or like ASAs. And so you have another option. Now, there are other considerations that go into play here. There's overhead involved, right? Because keep in mind, tunnel mode, we're adding additional encapsulation here. And so in addition to the IPsec, and the encrypting everything, we're adding in an additional layer 3 header. So make sure that you think about that. But typically, you're going to do tunnel mode, right? Tunnel mode's the mode you're going to do. And I wanted to make sure I covered that and the differences because we don't see that as part of our discussion here. In fact, am I already logged off? I am, unfortunately. All right. So we've created the phase 2 parameters. Now, what we're going to do is we're going to create the crypto map. And this is the map that's going to get applied to that outside serial interface on router 1. And the command is pretty straightforward. It's crypto map VPN map. And we'll give that map a number. And then, again, let me question mark this out here. And this is, well, how is this map, what parameters are we using? Well, we're using IPsec with Isocamp, right? And that's going to be, when we're doing the crypto map, it's pretty straightforward that is what we're going to be using. Now, under here, and you'll notice we get that little message telling us new crypto map will remain disabled until a peer and valid access list have been configured. So we have to have some sort of an ACL configured. So they want us to put a description in here, and we'll just say VPN connection to R3. And now here's where we put the mapping information so that IPsec and Isocamp know what they're supposed to be doing. So I'm going to set my peer to 10.2.2.2. And let's set the transform set we're going to use, because I could have multiple transform sets defined. But we're going to use the one that we just created with the ESP AES and the ESP SHA HMAC, right? Because the confidentiality and integrity are both provided for us with ESP. And it's the encryption that we get that we wouldn't get with AH. Okay, so we've got that in there. And now let's match not IP address, but the access list. What was the number of the ACL? And what about a named ACL? Could I do that? Sure. Again, we just used a number, but you could use a named ACL as well. That is the crypto map. That's it, right? We go in, we just put our description, we set who the peer is going to be, we point out the transform set, and again, these are all sort of the phase 2 parameters that we're, again, the Isocamp phase 2 parameters that we're referring to in the map. Because remember, phase 1 is about the keying material. Phase 2 is about the data plane, the package, right? What is it? I want to say the moving company analogy. It's all of that cargo that's in the moving van. That's what phase 2 is about. And so the next thing we would do is we would go to interface serial 000, and we would apply the crypto map, VPN-map, right? And you can see Isocamp is on. We'll say in, and let's save this in case, for whatever reason, that router reloads on us or we have an issue here with packet tracer. So Cisco con PA55 and then Cisco ENPA 55. So on router 3, we'll move through it a little more quickly here. So we're going to go do our transform set, crypto IPsec transform set VPN-set. And again, ESP AES because it takes care of the encryption component that AH does not. SHA-HMAC. And then we're going to do the crypto map. So we're going to say crypto map VPN-map 10 IPsec Isocamp. We'll put a description in here, VPN connection to R1. And here's where we need to be careful, right? Because remember, we're on router 3 and we're setting these things up for router 1. So it's going to be set peer to 10.1.1.2. The transform set, right, we know what that's going to be, VPN set. We created it earlier, and we use the same extended ACL number of 110. We'll get into interface serial 000, 000, and we'll apply the crypto map here. So crypto map, VPN-map. All right. And so we've done all of that. So now's where we get into the discussion about whether or not, and we'll say right mem, whether or not things are working, right? So great command to run, right? Definitely make sure you're looking at this command output. So we're going to say show crypto IPsec SA. And so what are we looking at here? We're looking at the security associations right, that we have for IPsec. These are the phase 2. And keep in mind, if phase 1 doesn't work, you will never get to phase 2. You're not going to get to phase 2. So when I say show crypto IPsec SA, we are seeing the phase 2 setup and what things look like here. And so here you can see we've got and it knows from the crypto map information, right? The source and destination, the local identity for router 3 is that network there. The remote network is router 1's network. Who's my current peer? And IPsec, we're using port 500 again. We're not doing NAT traversal here or anything like that, so you're not going to see 4500. So you see port 500, and then you see packets encrypted, packets not encrypted. And the interesting thing here is there's no traffic that's gone across encrypted yet. Well, that is about to change, and you can see, I think it actually makes a comment. Notice the number of packets, they're all set to 0, but now we're going to ping. So let's come on to PCC and let's ping over to 192.168.1.3. So now we're generating information from PCC, ICMP ping packets that are going to come to router 3, and they should be identified, and we'll probably have a couple timeouts here and then it should kick in. And what we should see when we run this command, oops, sorry, didn't want that. When we run this command next time, we should start to see that the packets are being encrypted, and we're not seeing that. Let's come over to PCA, and hopefully this isn't an order of operations thing. Ping 192.168.3.3. Let's see what router 1 says. Show crypto IPsec SA. And so that's still showing no traffic. So on router 1, do we see the packets more than 0? And we do not. But we are creating that interesting traffic, right? So this says uninteresting traffic. So we've got something's going on here. Something did not work as it was supposed to. Let me take a look here. So let's say show crypto Isocamp SA, right? So I'm looking at the phase 1. And so here's where we see, and this is great, because when things break, right, we get a chance to dig a little bit deeper. So this would be, so when I said IPsec, I was interested in the phase 2 information, right? When we're talking about Isocamp, I want to see the phase 1. What does that look like? And you can see here the main mode, right? That's what that MM means. And there's the destination 10.222, the source 10.111, and we're in the main mode, no state, right? And so that's not good. And this, again, could be packet tracer thing, but let me double check and let me make sure that I used the right IPs, 10.111 and then 10.222. So let's make sure, because it's got to be something with the IPs on my part. So router 1, 10.222, 10.222, and everything looks good there. Router 3, let's make sure that the IPs are correct. Show run. So 10.112, and that is correct. And wait a second, let me scoop back up here. Yeah, 10.112. And so what do you notice is not here, right? So just by looking at this, we can tell what's going on. What am I missing on router 3 that I have on router 1? And this is a great reason behind, and actually, I'm sorry, maybe it was before. Did I go right by? Oh, I actually went by it. Okay, sorry. I thought I was missing the key here. So the key is on here, VPNPA55. Let me make sure I didn't typo this here because I love doing typos. VPNPA55. So that is correct. So let's do this. Let's save our config here. And let's say write mem. And let me try to ping 10.2.2.2. All right, so we can ping over there. Let me see if I can ping 10.2.2.2, and then you know what? I have to go in the extended ping. I don't want to deal with that. To source it from, I was going to try to source it from the Gigabit Ethernet 00 interface, which would be that 192.168.1. But let's come back to the PC. Let's give it another try here before we ultimately do what I'm going to do, and that is going to be to reboot router 1. Because this is interesting traffic, right? This traffic should be matching that ACL in the crypto map And ironically, I looked over here at the percentage, and I think it's 90 something, and it thinks that something's wrong. Oh, ha, okay. Yeah, that would also make sense. You should probably apply the crypto map to the correct interface. So on router 1, it's serial 000. On router 3, it is not serial 00. And that is my problem. I have the crypto map on an interface that is not the interface where the crypto map should be. So let's go into interface serial 000 and say no, crypto map. And what was it? VPN? I can't remember the name of the map. VPN map? Yeah, I think we just called it VPN map. VPN dash, whoops, map. All right, so there we go. Int serial 001, and we'll say crypto map VPN dash, or no, sorry. Yeah, crypto map VPN map, VPN dash map. There we go. So now let's come back over here to router 1 and let's run that show crypto Isocamp SA. And it looks like we're still behind here. Let's see. Let's see if we can get some interesting traffic in there to bring it up. I was hoping it was going to pop up on its own there, but it's not. And again, we should get timeout, then it works. And instead of no state, we go once it's, and again, remember, this is phase 1. So phase 1 says, I'm in quiet mode, idle. Now, a lot of learners will think that when they look at this output, they'll see this and think, well, wait a minute, I'm passing traffic. How is it idle? Well, remember, this is phase 1 information. It's idle because the exchange of the shared keys has been done securely, and the phase 1 is complete. And until, and if and when, phase 1 needs to rekey, I will be QM idle because phase 1 has done its job. It's over with. Now let's go back to phase 2. And in fact, let me do this. I'm going to kick off a ping-t, which is an infinite peg. It's just going to go forever. And we'll say, show crypto IPsec SA. Let's look at the phase 2, the Isocamp phase 2 security association. And here's what we want to see. We've got 18 packets have gone encrypted and 18 have gone have been decrypted, right? Because we're sending ICMP echo requests, we're getting replies back, and they're all going into the tunnel. And you'll notice that we've got a little additional information down here. We can see the path MTU and the IP MTU of the tunnel. We can see the inbound ESP Security Association information here for this tunnel, and we can see the transform set. And remember, the transform set, you must have matches. You can have more than those two things in the transform set that are defined because that is negotiated. And I think I went right by that when I did the transform set. Remember, the transform set is going to be negotiated and the parameters need to match. So just like the phase 1 parameters need to match for the secure exchange of the shared secret, that keying material, the phase 2 parameters, they have to match. You can have more than these, but at least the two of them that you have in here would have to match. So what I'm trying to say is here on router 1, we said ESP AES and ESP SHA HMAC. Over on router 3, I could have every single possible thing defined. As long as those two are defined on router 3, this is going to work, right? This is going to work. And then you see the outbound security association as well, and the crypto map that's being used. And let's go down here. And so now this is what's going to be important, right? And so if I run that command again, you can see that, boy, the ping is running crazy, right? You can see I've got this ping running. Let me stop the ping. Do a Control-C here. And this PCB that we've been ignoring this whole time, this is going to be the uninteresting traffic because this is not going to match the crypto map. And it's not going to match the ACL in the crypto map because I'm going to originate this traffic from PCB. So let me ping 192.168.1.3, and let me do a ping 192.168, and let's do a ping-t here. Because here's what I want to show you. Let's come back to router 1, and you can see I've got connectivity, right? Perfect connectivity. Router 2 is not doing any IPsec tunneling at all. And it works because the return traffic is not matching the crypto map extended ACL that's looking for source of this network going to this network. What it's seeing is that is the source coming inbound, and then when it's returning, this is the source, but this network up here, PCB, is the destination. And so if I was to say show IPsec, take a look at that. No packets are being encapsulated. No packets are being de-encapsulated, right? Because the traffic is not matching the ACL. And you can see we're pinging like crazy. So let's do it in the opposite direction. You might be thinking, okay, well, that's because it's coming inbound. Here, let's say ping 192.168.168.2.3. And actually, let me do a ping-t. And you can see we've got connectivity. That connectivity is coming from PCA going out router 1. Is it hitting the crypto map? No, we're still at 115 packets, right? And again, remember, everything we did here was IKE version 1, IKE v1. We did phase 1 and phase 2, right? IKE and Isocamp phase 1 and phase 2 we did. And again, sometimes I hear phase 2 is the IPsec phase 2 because that's where you're dealing with the cargo encryption and integrity settings. But we did IKE v1 in this activity. And that's very important to point out. And we did crypto maps. And as I had mentioned, crypto maps are considered to be sort of a legacy approach to doing it because of the fact we've got to configure these ACLs. And so that is going to wrap it up for this activity. So to wrap things up here, right, at a high level, what have we covered? We covered the creation of the Isocamp IKE phase 1 settings to protect the keying material. We configured the Isocamp IKE V2, phase 2 settings in order to protect the data plane, right? Control plane phase 1, data plane phase 2. We talked about main mode in the 6 packets and the fact that the 5th and 6th packet are encrypted, and those are protecting that keying material and the pre-shared key exchange of information. And if you were doing certificates, protecting the certificates. We talked about aggressive mode, only has 3 packets. IDs get passed in the clear. It's not going to work in a secure environment. You're not going to want to use aggressive mode. And again, IKE v1 is main mode and aggressive mode. IKE v2 does not have those modes. It's got different modes. And then we talked about the phase 2, where we were using the ESP algorithm, that AH does not provide confidentiality. The C is not there. We talked about ESP IP protocol 50, Authentication Header IP protocol 51, that they don't have ports. ESP and AH do not have ports, but they're layer 4 protocols. So unlike TCP, UDP, and ICMP that you find at layer 4 where you would have, or TCP and UDP specifically, where you'd have port information, ESP and AH do not have that. When you're doing one-to-one NATing, AH is not going to work because it is looking at those immutable fields, the source and destination IP, to see if they've been changed. And if they have, AH is going to say, hey, whoa, that's my job. I'm here to protect the integrity of this packet to make sure that nothing's been tweaked in transit. And it has. So with NAT, no go. ESP is interested in layer 4 and above. But who's doing one-to-one NAT for everything in their environment, right? Typically, enterprise environments, you're going to be doing port address translation. And what changes when you're doing PAT? Yeah, the ports, the layer 4 information, right? That's how port address translation works. The ports, that's the P in PAT. And so ESP doesn't have ports. And again, AH doesn't have ports either. But you can do NAT traversal, and we looked at RFC 3948 or 3947. I think both of those cover NAT traversal. But that's how NAT-T works, is it encapsulates everything into a UDP packet, port 4500. So there's your port, right? And you can do IPsec over UDP, port 4500, and that's going to allow that to work for you. And so we've covered quite a bit in this activity, again, laying the foundation for the next two videos we're going to look at. We're going to be looking at a static virtual tunnel interface using IKE v1, and then we're going to do a static virtual tunnel interface using IKE v2. And then I'll even do a third video, so I'll do 3 videos. And then we'll do GRE over IPsec. Because remember we talked about GRE, right? IP protocol 47, GRE has no protection for the information in a GRE tunnel. It's all in the clear. And so typically when you're running GRE tunnels between sites over the internet, you want to protect that information. And we can do that using the IPsec suite of protocols. ESP, AH, IKE, Isocamp, all those wonderful things that make IPsec up. And the one key takeaway from this video, remember, IPsec is not a protocol. It is a suite of a framework, if you will, that includes all of these cool protocols like ESP and AH. All right, well, that is going to do it for this video. Thank you guys so much for watching, and I hope to see you in the next video.